All right, so we left off here with the problem that we have this nice equation. We have our sample mean, we have our critical value of z, we have our sample size, but we didn't have the population standard deviation that we needed to calculate this standard error term that would tell us how spread out our sampling distribution is around the mean. Because of that, we're going to use a tweaked version of this formula that uses something called the estimated standard error. And I'm just going to write this out. And as you'll notice, it looks really, really similar to the main confidence interval formula. I'm going to have x bar plus or minus z times s over the square root of n. So the only difference here is that we are taking our population standard deviation value here, and we're substituting it with s. And if you remember way back a couple weeks, s refers to the sample standard deviation. But I just want to take a quick moment to say that this whole term is going to be considered your estimated standard error, which we write as s sub x bar. So again, just to recap what I did here, we're going to be using an estimate of our standard error here, which we call s sub x bar, instead of our standard error that we had in the original formula, because typically when you're doing this kind of work, you don't know, what this value is. So I'll just rewrite this out so you can see everything that goes everywhere in the formula. Where x bar is your sample mean, z is your critical z value, which again we know based on the properties of a standard normal distribution, and which you can find in the table that's on the slides. N is our sample size, and s is our sample standard deviation. So where do you find the sample standard deviation? Well, the same place that you find the sample mean. So in any problem like this, I will give you these values. And the idea would be that you take a sample from the population, you can calculate the mean, and you can also calculate the standard deviation. Luckily for you guys, we are past the point where you have to calculate that by hand, but it would be the same kind of standard deviation that you calculated earlier in the semester when we learned about what the standard deviation was. So I'm going to come back to this example and write out everything you'll need to know here. This is point 2 from the lecture on the next page here. So we have a sample of 100 people with robbery convictions. We have which is our n, mean sentence length of 10.6 years. And one more piece of information that we would be able to get from our sample is the standard deviation. So we're going to say we have a sample standard deviation of 5.8 years. And so these are all values that will always be given in problems like this. Again, you're imagining you take a sample of 100 people, and then for those 100 people, you calculate a mean and you calculate a standard deviation. Once you have those things, you have everything you need to calculate a confidence interval. So we have x bar is equal to 10.6. We have s, which is equal to 5.8. We have n, which is equal to 100. And we have our critical z value, which is always going to be equal to 1.645 for a 90% confidence interval. And again, that number would change if you were looking at, say, a 95% confidence interval or a 99% confidence interval. So now we're going to take our nice confidence interval formula and plug stuff in. So our confidence interval formula using estimated standard error is going to be given by this, where you have your sample mean, which is 10.6, plus or minus your critical z-value, which is 1.645, times your sample standard deviation, which is 5.8, divided by the square root of your sample size, which is 100. And from here, we're just doing the math. So this will come out to 10.6 plus or minus 1.645 divided by 0.58, or 10.6 plus or minus 0.95. So this is one way that you could write your answer, but the way that I'll ask you guys to write it that I think is a little bit more illuminating is to write it in terms of the interval. So as I said before, we were trying to find the interval around 10.6 that is likely to include the sample mean at some 90% probability. To find either end of this, we're going to take our 10.6 plus or minus 0.95. The higher end is going to be 10.6 plus 0.95, which comes out to 11.55. And our lower end is going to be 10.6 minus 0.95, which comes out to 9.65. And we have our interval. And what we can say about this now is that we can be 90% confident that an interval from 9.65 years to 11.55 years includes the true sentence length for robbery in the population. And I'll write that out in a second, but another way that you can write this confidence interval is 9.65, comma 11.55. And this is referring to what I showed more graphically here, which is that the confidence interval ranges from 9.65 to 11.55. And again, we'd say we can be 90% confident that an interval from 9.65 years to 11.55 years includes the true population mean. All right, so there we have it. We have our confidence interval. And so again, this is this buffer around our point estimate that tells us at some level of certainty, where we're likely to find our population mean. And I'm going to go through one more quick example here, since in this last example I was kind of showing you the steps of where all these different things came from, but in actually calculating one of these, it's a lot quicker. So I'm going to go through one of these quickly just to demonstrate that as well. So here's our second example. So we have a sample of 40 police officers with an average of 16.3 arrests in the last month, and a standard deviation of 4.1 arrests in the sample. So here we're describing a sample. It's a sample of 40. We have a mean of 16.3 and a sample standard deviation of 4.1. So this is all information about the sample. And we're going to find a 95% confidence interval to estimate the true number of arrests made by police officers in the population. So before filling in the formula, I'll just write out all these different components that we need for the formula and what they are. So one thing we need is the sample mean. This is 16.3 based on the information above. Another thing we need is a sample standard deviation. That's 4.1 based on the information above. We also need the sample size, which is equal to 40 based on the information above. Our last component is the critical value of z. And as I said before, the critical values of z are always going to be the same for each of the different confidence levels that we're talking about. And for a 95% confidence level, your critical value of z is always going to be equal to 1.96. And again, you can find these in the table that's on the slide. So z is equal to 1.96 for a 95% confidence interval. And these are set in the same way that that 68, 99, 95, 99.5 rule is. So you just look at the table to find your critical value of z here. Now we're going to plug stuff in. Our confidence interval is going to be given by x bar plus or minus your critical value of z times your sample standard deviation divided by the square root of your sample size. Plug in what we got. We have 16.3 for our sample mean, plus or minus 1.96 for your critical value of z, and we're multiplying that times 4.1, our sample standard deviation, divided by the square root of 40, which is our sample size. And if you do all this math out, you get 16.3 plus or minus 1.96 times 0.65, and this comes out to 16.3 plus or minus 1.96, plus or minus 1.27. Gonna write this in a whole new line. Comes out to 16.3 plus or minus 1.27. So here is your answer, but again, I'm going to ask you that you write it in interval form. So we're going to actually add and subtract out 1.27 from 16.3 on either side. So we want to find what's the buffer around this point estimate of 16.3 that likely includes the true population mean. So to get there, we're going to do 16.3 plus 1.27, which comes out to 17.57. And over here, we're going to do 16.3 minus 1.27, which is going to give us 15.03 on this side. So our confidence interval can be written as 15.03, comma 17.57. And we would say we can be 95% certain that the interval from 15.03 to 17.57 arrests includes the true population mean. So that's it. That's how you find a confidence interval. And like I said, it's a lot quicker when you actually just sit down and plug everything in than when you go through all the different steps. And so it tells you that you can be 95% certain that this interval you found includes the population mean. And in other words, if you were to do this 100 times in a row, this interval that you found would actually overlap with that true population mean 90 out of those 100 times. Right. And as I said before, these examples that I gave apply when you have a sample size that's larger than 30. So I'm going to end this lecture by talking about what to do when you have a small sample size, and also introducing another kind of probability distribution, or sampling distribution, that will also come up in a couple of weeks after this. So we're going to go back to the slides one more time.